All right, L'Hopital's rule. Now I've put this in the limits chapter. I'll probably put it elsewhere also because it's a limits problem, right? If you walk up to this thing and look at it, you're just going to say, hey, that's a limit problem. I'm going to use my limit techniques. So that's why it needs to be in the limit chapter. But the thing about L'Hopital, I think he's French, is that he was, other than being French, is that you need derivatives to use L'Hopital's rule. Like the whole point of L'Hopital's is that by taking some derivatives, we'll be able to figure out the limit of something easier than with the other techniques. So if you're seeing limits for the first time and haven't done derivatives yet, you'll need to go ahead and do derivatives, at least for some basic stuff, before you can do this. That said though, if you've already had derivatives or know what they are, this is actually awesome. And the reason they teach you this after limits is because it's going to make every limit problem way easier. Because it's sort of like a one size fits all. Do this every time, it works for everything. And that's what is awesome about L'Hopital's. So let's get to it. Here's the deal with L'Hopital's. It's only valid if your original problem, because remember the first step that when we do limits, we always plug and chug, right? We always just say, oh, maybe it'll work out if I just take that 2 and plug it in for x. But what happens when I do that on this one? Well, I plug in 2 here, I get 4 minus 4 is 0, and I get 2 minus 2 is 0. And those are what always happen, right? Because otherwise it would be a really boring problem. So teachers don't tend to give ones that turn out nicely at this point. 0 over 0, that's called indeterminate. And we figured out we had to do something, right? And the old way we would have done this was just taken, factor the numerator and canceled out the x minus 2's or something. It sort of like had to be a contrived problem. But it's going to turn out this actually works anytime there's a 0 over 0 indeterminate situation. It also works if we have infinity over infinity. So if you look at this one, if you plug in infinity, top and bottom, you're obviously going to get infinity over infinity. Indeterminate and L'Hopital's also works for infinity over infinity type indeterminate situations. And of course, this is one you might recognize as a special limit that we learned in the limit rules chapter. But same thing, sine of 0 is 0, and x is obviously 0 as well if we're approaching 0. So that's why plugging in wouldn't work for these. These are sort of classic indeterminate situations that you'll need to do something on. And I'm telling you, L'Hopital's is the way to go. We cannot use L'Hopital's though if it's not indeterminate. So if plugging in would work the original time, it doesn't count. So you'll notice right now, this is the same problem we saw a second ago. We switched from x approaching 2 to x approaching 1. And now when I plug in directly, it works. I get 1 minus 4 over 1 minus 2. Just negative 3 over negative 1 is just equals 3. So at this point, we're done. And L'Hopital's is not necessary because when you just plugged in, it worked. And that's really important because it turns out if you use L'Hopital's on one of these ones that already works without it, you'll actually get the wrong answer. So L'Hopital's is sort of like this amazing tool that can get almost any limit problem right very easily. The downside is if you use it when you're not supposed to, or when you didn't need it, it's actually going to give you the wrong answer. So you're not just wasting your time, you're actually going to get the wrong answer. And that's why you got to be super careful not to use L'Hopital's unless you've already tried plugging in. Same thing with this one. This is a slightly trickier one. It might not be so obvious that we don't need L'Hopital's. When we plug in 5, we just get 3 over 5 minus 5, which is 0. This is not indeterminate. This is just no limit. Or limit does not exist, however you feel like writing it. Or infinity, this increases without bound. But the point is that it's actually not infinity even, it just does not exist. Because it shoots to positive infinity on one side and negative infinity approaching 5 from the left. Or vice versa. Point is that it does not exist, no limit. So if this had been 0 over 0, great. But 3 over 0, that's just no limit. Same thing on this one. Now we're approaching pi instead of 0. And this is a classic trick question they can burn you with. That special limit where sine x over x goes to, becomes 1 or something, that only works when x is approaching 0. When x is approaching pi, we just plug in sine of pi and we get 0. And then denominator is pi. And that's just 0. 0 over pi is just 0. Something divided by 0 is undefined or does not exist. Again, two situations where L'Hopital's will mess you up if you try and use it. So just be really careful. Unless you have 0 upstairs and downstairs, it's not a L'Hopital's indeterminate situation. All right, but once we did figure out it is L'Hopital's, we plug in, we get 0 over 0. So like on this one, plug in 2, you just get 4 minus 4 is 0. 2 minus 2 is 0. So sure enough, this is indeterminate, and we can use L'Hopital's. So here's what L'Hopital's does. All we do is we take the derivative of the numerator and the derivative of the denominator separately and just try plugging in again. So what this says is that the limit as x approaches 2 of this expression is the same thing as the limit as x approaches 2 of the denominator of x squared minus 4, which is just 2x, over the denominator of x squared minus 2, which is just 1. So you see what I did there? I just took the derivative of the numerator and put that right here, and I took the derivative of the denominator and put that down there. I did not use the quotient rule. So I did not use the whole uv prime minus vu prime over v squared thing. I just took the derivative of a polynomial and put it over the derivative of another polynomial. So L'Hopital's, we're not taking the derivative of this whole hunk of junk. All we're doing is taking the derivative of the numerator and denominator separately. And that's really important. But that's also what makes it so easy. But now you can see that, hey, if I just plug in 2, it works now. Because now if I get 2 times 2 is 4, and 1 is just 1, there's not even anything to plug in. So I get an answer of 4, which is what I would have gotten if I used one of my older techniques. If I had factored the numerator and canceled x minus 2's, I would have gotten x plus 2, which is also 4. So L'Hopital's appears to work. Let's try this one. You can see that if we plugged in, just plugged in negative 3, we'd get 0 over 0. You can try that on your own right now if you don't believe me. So we can use L'Hopital's. So all we're going to do is we're going to keep the limit as x approaches negative 3. Don't change that at all. All we have to do is just take the derivative of the top, which is going to be 2x plus 1. Derivative downstairs is just 1. And plug in again. So we get negative 3 right here. It's just negative 6 plus 1 is negative 5. Over 1 is just negative 5. Pretty crazy, right? Good stuff. And that's why L'Hopital's is so fun and easy. Here's another one. First things first, we got to make sure that it actually works. The L'Hopital's is relevant. So first we have to try plugging in. But if you plug in infinity, for x here, you see you can get infinity over infinity, which is indeterminate, and therefore we can use L'Hopital's. So the derivative of the top is 2x minus 2. And downstairs we have 2x. All right, let's try plugging in infinity again. Oops, we still got infinity over infinity. We haven't helped ourselves, right? So that means we can just use L'Hopital's again. So you can keep taking the derivative again and again and again. Do L'Hopital's as many times as you want on the same problem. So take the derivative again. Derivative of 2x minus 2 is just 2. Derivative of 2x is just 2. So 1. Now you can see there's not even any place to plug x into. The limit is just 1. Pretty cool. So L'Hopital's, you can use it as many times as you want. Kind of zany the way that works. All right, so let's try taking a crack at a couple of ones that used to require special rules. This is from those like limits of trig problems where they told you, hey, given limit of sine x over x as x approaches 0. They told you, I think that was 1, and the limit of this other thing was 0. But now we're going to actually figure this out with L'Hopital's. Super simple. So first of all, we try plugging in, and sure enough, sine of 0 is 0. So we get 0 over 0 if we just plug in 0 to both x's. So we take the derivative of top and bottom. Limit as x approaches 0. Limit of the derivative of sine x is just cosine x. And derivative of x is just 1. Cosine x. So now we can just plug in directly, because now downstairs we just have a 1. Upstairs, plug in 0 and you get 1, because cosine of 0 is 1. So we just proved, essentially, I mean, we didn't quite prove it, because who knows if L'Hopital's really works, but the point is that's the same answer we got back in that old chapter. They just told us that, hey, limit as x approaches 0 of sine x over x is always equal to 1. And we just showed it with L'Hopital's. That gave us the same answer. Pretty nifty. Same thing will happen here. If we plug in 0 right now, we would get 0 over 0. So we'll take the derivative of top and bottom separately. So we'll get derivative of 1 minus cosine x. The 1, just derivative of 1 is 0. So we'll get negative, and then the derivative of cosine is actually a negative sine x. So these negatives will cancel. And then derivative of x is just 1. And now we can just plug in 0, because downstairs at this point we have 1. So this is no longer indeterminate. And we'll just plug in 0, and we get 0 over 1 equals 0. Pretty crazy. Yeah, L'Hopital's is wonderful. And I think the reason they teach it last is not only because you need derivatives, but it's also because it would make all the math they made you do seem irrelevant. I mean, if you had just learned L'Hopital's right off the bat, you could have saved yourself, what, like 2 or 3 weeks of limits homework? I don't know, it frustrates me to no end that they do it that way, but obviously calculus is about making you do a lot of algebra and a lot of sort of tricks. So that's just one trick they wanted you to have to learn how to do the hard way first. All right, here's a couple of limits that we just didn't even know how to do before we learned L'Hopital's. Because there is no, if you plug in 0, you get 1 minus 1, which is 0, over 0. So this is indeterminate, but also there's no tricks we could have used. We don't have a special rule for exponentials, and we don't, there's no trick we learned in that previous limits chapter about how to solve something like this. But if we use L'Hopital's, which always works for 0 over 0 situations, all you have to do is just take the derivative of top and bottom. So this is going to be the limit as x approaches 0 of that 1 goes away, and we take the derivative, so we'll just get negative e to the x, because the derivative of e to the x is just e to the x. No chain rule required, since that x is just x, not x squared or anything. And derivative of x is just 1. So now we can plug in 0, no problem. Plug in 0, you get negative, and then e to the 0 is just 1. Because anything to the 0 power is 1. Let's take a crack at this one. So hopefully you'll see that if you plug in infinity, the natural log of infinity cubed is still infinity, and infinity squared is infinity. So it's infinity over infinity. Sure, we have x cubed, we have x squared, but the point is two enormous numbers increasing without bound divided by each other. So that is indeterminate, and we can use L'Hopital's. What's the derivative of the natural log of x cubed? Well, the derivative of ln u, so d over dx, of ln of u is just 1 over u times u prime. That's the chain rule version of the natural log derivative. So, now keep in mind, this is not a quotient rule. It's just take the derivative of the top and bottom separately. So we still have the limit as x approaches infinity. But now the derivative of ln of x cubed is going to be 1 over x cubed times the derivative of u, u prime here. So that's going to be the derivative of x cubed, which is 3x squared. And downstairs we just have the derivative of x squared, which is 2x. So this is some algebra, but basically this x squared is going to cancel that, and we'll just have 1 over x. So we'll have 3 over x as a numerator, and downstairs we just have 2x. All right, and this is still limit as x approaches infinity. So what happens at this point? In each stage, before we do L'Hopital's again, we need to try plugging in and just see if it works. So what's the limit as x approaches infinity of this thing right here? Now this is a really tricky one, but if you plug in infinity to the numerator, you get 3 over infinity, which is just 0. But then downstairs, you still have infinity, because 2 times infinity is just infinity. So actually, we don't need L'Hopital's again. This is just 0 over infinity, which is 0. Another way you could have done this was 3x over 2x. I'm sorry, 3 over x over 2x. This, you could divide. Anyway, just if you divide this out, that x actually ends up down here, so you'll end up with 3 over 2x squared if you simplify this. And of course, the limit of that, you can see right away, is just 3 over infinity, which is, again, 0. All right, so that's L'Hopital's. There might be lots of different variations of problems on this. It's just that most students don't really have much trouble with it once they realize, oh, all I have to do is take the derivative of the top and bottom separately. That's easy. No quotient rule, nothing like that. The next video is going to be about a very hard type of problem. We're going to use L'Hopital's, but also some really fancy natural log trickery. So do not do the next video unless those types of problems are in your class. However, whether you're in an AP class or an easy college class, a relatively easy like calculus for business majors class, I've seen it in all levels. So the problems in the next chapter, sometimes they show up in easier calculus classes. They definitely show up in harder calculus classes. So definitely check your syllabus and ask your teacher if that type of problem is on there. You'll see what I'm talking about next.